Hello everyone, welcome to the 9th video in this series. We start with problem number 81. A particle is confined in a one-dimensional box between x equal to minus a to x equal to plus a and is in its ground state. Suddenly the walls of the box are shifted to x equal to plus minus 2a. The probability that the particle is now at the first excited state of the new potential is. So we know the ground state of a particle confined in one-dimensional box is given as cos of n, that is 1 pi x divided by 2a, and the first excited state wave function of box of length 4a is something like sine 2 pi x by 4a. So this is essentially pi x by 2a. So we have to take the integral of phi 2 star phi 1 dx from x equal to minus a to plus a. So we have integral containing sine and cos functions. So due to their orthogonality, the integral would be 0. So option D is the correct answer. Problem number 82. A quantum mechanical harmonic oscillator is in the state psi, which is given by this, with the angular frequency omega. We have to find the average energy of the system. So the average energy of the system is given by sum over I Ci whole square times Ei. The Ci's are the coefficients and Ei's are the eigenvalues for the energy eigenstate. Ei is equal to E plus I plus half times h bar omega. So let us calculate the average value. So this is equal to 2 by 16 times the energy corresponding to the state 0, that is half h bar omega, plus 4 by 16 times 3 by 2 plus 1 by 16 times 5 by 2 plus 9 by 16 times 7 by 2. If you calculate this will be 2.56 h bar omega. So option C is the correct answer. Problem number 83. The Hamiltonian for an n-state system is given by this, where k and j are orthogonal basis vectors. The energy eigenvalues Ej's are given by. So one of the way to do this is to consider a value of n. Let us take n equal to 2. Thus the Hamiltonian is given by E naught times 1 1 plus 1 2 plus 2 1 plus 2 2. So if you take this ket as 1 0 and this ket as 0 1, the Hamiltonian can be written in a matrix form such as this. And let us now calculate the eigenvalues of this and see which of the following option is correct. So to find that, we find the trace of the matrix. The trace is 2 times E naught and the determinant is 0. So if the eigenvalues are lambda 1 and lambda 2, then lambda 1 times lambda 2 is equal to 0 and lambda 1 plus lambda 2 is equal to 2 E naught. Thus we find one of the eigenvalue is lambda 1 equal to 2 E naught and other one is 0. So let us now match with the options. So option D says Ej equal to E naught. So this is not correct. Option C says E naught equal to 0. Yes, we have one of the eigenvalues equal to 0, but Ej is equal to J E naught. This is not correct. Option B says Ej is equal to J E naught. This is also not correct because we have a 0 eigenvalue. So option A, which says that E of n is equal to n E naught. Essentially we have E of 2 is equal to 2 E naught. this is same as this, and E of j, that is E of 1, is equal to 0. So option A is the correct answer. Problem number 84. A particle of mass m is in the ground state of a 1D harmonic oscillator potential with angular frequency omega. The entire system is placed in the center of one-dimension box of length this. The ground state energy will increase. For example, see this paper. So I am now quoting their words. For the ground state, the energy continuously increases from half h bar omega to infinity as the length of the wall decreases from infinity to 0. So option B is the correct answer. Problem number 85. If Vs is the stopping potential of the photocurrent I generated by shining a light beam of frequency nu to a metal surface, then which of the following statements is true? So the stopping potential V of S related to the frequency of the incident beam as follows: V of S is equal to h times nu. So it increases by increasing nu. Option C is the correct answer. Problem 86. 5 non-interacting identical spin 3/2 particles are in the one-dimensional harmonic oscillator potential. The ground state energy of the system is. So the spin is j equal to 3/2. Let us find the m values. That would be minus 3/2, minus half, plus half, and 3/2. Since these are fermions, so no two particles can be in the same state. So in the harmonic oscillator potential, let's say this is the ground state and this is the first excited state. 4 particles can be located in the ground state with different values of m. So let us draw such cases. So this is m is say 3/2, and this would be half, this would be minus half, and this would be 3 by minus 3/2. Same is true for the state 1. So now let us find the ground state. The ground state would be when 4 of the 5 particles are located in these 4 states and one of them is located here. So thus the total energy is 4 times half plus 3/2 h bar omega, which is 7/2 h bar omega. So option A is the correct answer. Problem number 87. Two angular momenta L1 and L2 are added to form J. If the eigenstate of L12 are denoted as L, m and those of J as J, mj, then Jm cannot be written as a direct product of L1 m1 direct product with L2 m2 because we know Li squared commutes with Lij. So let us now find Jz commutes with L1z or not. Since Jz is L1z plus L2z and Liz commutes with Lzz, so this is equal to 0. So this is not the correct answer. Now J square commutes with Jz, so B is also not the correct option. Jz commutes with L1 squared because Jz is essentially L1z plus L2z and each of these commutes with L square. So option D is also not correct. So option C is the correct answer. J square does not commute with L1z and L2z. Problem 88. A particle of mass m is trapped in an infinite quantum well of width L. The expectation value of its momenta in the third excited state is. The particle is going nowhere, so the expectation value of momenta in particle in a box is always 0 for any state. So option C is the correct answer. Problem 89. Consider the free energy as a function of order parameter m as this. The discontinuity of the specific heat at Tc is, so we first find the equilibrium value of m by taking the derivative of f with respect to m and equating it to 0. So let us do that. So we have minus alpha T minus Tc m plus b m cube is equal to 0. One of the solution is m is equal to 0, and we are interested in the other two solutions. M squared is equal to alpha T minus Tc divided by b. So let us now put this value of m squared in f. F mt minus f naught is equal to minus alpha T minus Tc divided by 2 times this plus b by 4 alpha squared T minus Tc whole square divided by b squared. So we have minus 1 by 4 alpha squared T minus Tc squared divided by b. The discontinuity of the specific heat can be calculated by taking the double derivative of the free energy with respect to T at Tc, and this is equal to minus alpha squared by 2b. So option A is the correct answer. Problem number 90. Suppose an ideal gas is having a transition following V P cubed is equal to constant equation. Initial temperature and volume of the gas are T and V respectively. If the gas expands to 27 V, then the temperature will be, so it's given that V P cubed is equals to constant C, and we use the ideal gas equation PV is equal to RT to eliminate P here. So V times RT by V whole cubed is constant, or T cube is proportional to V squared. Thus T1 cube divided by V1 squared will be same as T2 cube divided by V2 squared, or T2 will be V2 divided by V1 to the power 2 by 3 times T1. So here V2 divided by V1 is 27. So we have T2 is equal to 9 T1. So thus option A is the correct answer.